Assalamualaikum. Morning. So for today class, it's synchronous mode. So we go through this recording and we cover the cascade analysis. And next week we cover gas system cascade analysis. There are two type of gas cascade. The one that we learned today is on normal concentration. The next it's based on time-based speech. We call it SCA. SCA reflecting gas system cascades. But for today, it's subjection gas cascades. Almost similar to water, but bit different. So today, it will cover a comprehensive, rigorous examination of chemical process integration technique used to maximize resource conservation through structure, work example, self-check question, and elite readiness practice assessment. Because I put that quiz for today as well. Is number quiz number 5. Recording for yesterday also uploaded. So you try each of the activity. Activity is either, for example, 53 for the first meeting. So this is a self-paced study module. So the process integration represents a major shift for informational points of treatment strategy, which is true of what the gas. So by looking at the plant as a unified interconnected network, we can determine the exact thermodynamic minimum amount of fresh resources needed to satisfy the demand in designing any recycling pipe. So this today this mode study mode is to cover at least 2 hours study block. We need another 1 hour is for the exercise. I already uploaded the workbook as well for GCA and GASCA. It's not similar to yesterday WGA. But show you what is the difference in dress on. Okay, let's get it. So the process integration images an effective tool for resource conservation and emission reduction in water using network, which we learned yesterday. However, directly applying water pinch algorithm, meaning if we use the same method as the water pinch algorithm or pinch analysis, Utility gas system failed due to two fundamental thermodynamic operational differences. So two reason why you cannot use water cascade analysis to analyze the gas system. First one is impure fresh feed. So the standard water pinch synthesis assume pure fresh water, zero contaminant with available is available. So meaning water that came into the system is like yesterday, actually zero impurities, meaning zero ppm, only water. In utility gas system, so nitrogen, oxygen, hydrogen distribution, the fresh gaseous supply frequently contain measurable impurities. So to really receive a very pure gas is like not possible. There will be some impurities like 5% nitrogen, 5% argon due to production constraint or academic because very, very pure gas is expensive. GCA is designed specifically to handle impure fresh feed seamlessly. So the method that you learn today, cascade analysis, is for gas only. You cannot use it for water. Yeah, I haven't checked it or try it, but yeah, just stick with gas for GCA using its own algorithm for WCA, its own algorithm. The second reason is fixed in the sink and operating pressure. A water sink flow rate can often fluctuate as long as it's transfer the targeted mass lot of contaminant. In contrast, utility gassing such as gas phase hydrotreating or chemical reactor represent continuous, rigid, volumetric operation to maintain uniform steady state operating kinetic and system pressure. Each gas consuming process must be supplied with a strictly uniform inlet mass flow rate and gas concentration. So meaning unlike water, the sink or sink mean there's a source and sink. So sink mean the demand, yes, the demand. So that demand must be say, uniform and steady because you are channeling the gas into the system. So for let's say for the reactor or hydro treating, they need certain fixed amount to do the direction, correct? So GCA uses an interval-based algebraic cascading technique to set the absolute minimum utility gas target prior to network design. So this today class is based on a paper written by Professor Fu from Nottingham University, Malaysia. So you can see the paper. I don't remember the number of the paper, but it's under graphic number 3. So the paper entitled Setting the Minimum Utility Gas Flow Rate Target Using Cascade Analysis Technique. So this is the GCA numerical targeting algorithm. There are 5 steps. Yes. The first step is to arrange the concentration level. So this is similar to water cascade. From 1 to 6, then concentration similar to water cascade, although it's in percentage. For water cascade, it's in ppm. So step 2 is establish the net internal net flow rate for each concentration level K. Calculate the net flow rate, sigma Fi minus sigma Fj is 2. So J is sink, Fj is sink, source is Fi. Then Fi minus Fg. Step 3, infeasible gas flow rate cascade. So start with 0. So assuming zero fresh gas supply, so normally it will start with zero any cascading method before we identify, because we assume no fresh gas required, then we find the picture. Cascade the net flow rate downward. So FCK go to FCK management plus, so this one cascading like this, this with this infeasible gas flow rate cascade. Sorry, interval net flow rate. So interval net. So 0 to the end. Therefore, priority load cascade. Delta M equation to the M. Okay. So delta M is equal to FCK times CK minus CK1. Sum this down to obtain the relative impurity load the cumulative delta M. So this is the equation. Actually, in what delta M is the component product. So multiplication of FC and the concentration different and plus the two concentration level delta C. Right. So the delta C here, yeah, that is, yeah, you need to find out. We calculate or add another column here for the delta C. So delta C is in between. So in this case, yeah, 0.1 right by 100, because this is in percent, and you get delta C equal to 0.001 times FC, then you get equal to 0.006. Then you do the cascading for the cumulative delta M. So how many cascading you need to do? FC with the interval net flow rate and going to delta M. Based on the delta M, of course. Cascading. So when you do the cascading, there is no number here. When you do the cascading, then it's appear the number based on the cascading, and you can so each level have their own number after you do the cascading. So initially there is no number for that quality delta M and the frequency. Last is identify minimum fresh utility, and then calculate the interval fresh gas flow rate when using FFK equal to cum delta M relative delta M over, okay, divided by CK minus CM. Right. So in this case, CF is fresh fruit concentration. So CF in this case is zero. You start with zero, right? But later on, when we identify the pinch, you need to calculate and during that time CF is zero. Some number. So that is the five step. GCA numerical targeting algorithm. Okay, so now we go for GCA what case study. So this work case study illustrate the application of GCA to a magnetic tape manufacturing process utilizing the nitrogen utility gas to maximize recycling and nitrogen reuse. The source stream must be segregated at membrane 3 deposited and 1.9% solvent. Dryer exhaust with 5.8. Dryer exhaust. Okay, dryer exhaust 0.5, 0.4. The fresh nitrogen supply is solvent free. Fresh nitrogen supply here. This is solvent free also the or meaning it's a no improvement. Yeah. But before one can construct this table, the first thing you need to know is similar to WCA. You need to this create this limiting data. So identify the sink and the source. So sink here is a drying 5.5 kg. Drying 5.5 kg. 1.8. This one the source. Just to be that. 5.5 0.4. So meaning the nitrogen point into not pure. Yes. You just said, yeah, you can have it. But all it's must be pure, but they are tolerant. So in this case, for coating and drying, the tolerance is between 0 to 0.2, 0 to 1. So to get very, very pure, it's, it's not impossible, but very expensive. So why not we increase the target 0.2 and 0.2, which is why it's not zero. If what if you Choose zero. Yes, can. No problem. Then once you have this data, you may construct this table two which is like this perspective. So the peak negative interval and fresh peak flow rate is negative 5.625, which occur at level 4. Therefore, the absolute thermodynamic minimum fresh nitrogen target is 5.60 per kg. So meaning this is the pinch. So this pinch is the amount of nitrogen, minimum fresh nitrogen required or target or introduced into the system. Instead of zero, this is the minimum. By cascading this fresh flow rate back into the table, we achieve the feasible cascade table shown. So by introducing flash fit of 5.65 here, you will get the pinch at level 4. So what we need to do, we need to calculate. Yeah, like this. Like calculate. Uh, so the discharge flow rate is similar to one enter 5.65 enter 5.65 discharge. So this is different compared to WCA. A lot, uh, maybe 10 ton per day going in, but going out much more than the and what wastewater produces much more than the fresh water introduced. Okay. So as a synchronous student, tip for solving is vital for reinforcing the theoretical concept. Uh, uh, Review the GCA case study on oxygen integration. One will refer to example two in full 2006 paper. And then an hydrogen integration example three. Example three. Yes, example three. Mm, grab pen and try to solve the following conceptual task will simplify reading the solution. Okay. So this is the oxygen integration. So your task is let's show you this one. So this is your task. First one is to in a feasible nitrogen GCT table two. This is still hydrogen integration. Example one, in the same paper, the pitch occur at 0.4%. Two, level four, the pinch dividing line separate the two main design region of pinch. Visit or below pinch access. Step the primary rule of network design when connecting sources to sync across the pinch. Second task for you to try in hydrogen multiple pinch problem with four. There are two pinch points with the pitch at 1.7% and the secondary pitch at 5%. You are evaluating maybe 25% if I'm 90% when you end up basically you get 20% percent productivity. So the question is this is example for mm, why does the membrane unit yield zero pressure reduction? Why the PSA unit reduces pressure energy by 6%? Okay. So for hydrogen oxygen integration, yes, it's on the paper. The following case study is an attempt to explore the interaction of possible site-wide integration between process section from maximum oxygen hydrogen. So the relative small portion of oxygen is also a factor to enhance or we understand this purpose. So there are fresh oxygen coming in. This sources is smaller. Okay. How many process? Okay, let me specify. So 41 feet per second, this is the purity with 5% impurities. So goes to the first process 25 kg, second 30 kg per second, which is 2. What per G per second for combustion, 2 kg per second for wastewater treatment. Yeah. Then from process 1 and 2, is discharge and this is we call it mass transfer. This is the non-mass transfer. So what happened is discharge at 10 kg per second with this of 40%. So this one is a pure oxygen, expensive oxygen. They just discharge it, although it's still 40% percent is so relative. Okay. Mhm. So first thing need to do limiting data. So we identify the sink and source. For sink, there are how many? Four. sink, demand, sama lah. Then for source, there are two from process one and process two, and fresh supply to be determined. How? Oh, the one you came with. You can refer to that. But why don't you try this first? Obviously, yeah, you have the example, sorry, the answer here, but how to get to this answer with what is, yeah, refer back with it. Sure. So you this half step. Yeah. So the GCT for this case study, table 5, give the first students apply discharge the P kg per second. So displacement fresh injection of into 7%. Mm. So when you do this, you should start with zero first, then you find the pitch. Yes. So meaning there are one value here, negative 30. So that negativity is located at level 3, concentration 40%. That's why there's a pinch here. Yes. So since this process is, let's say, include non-mass transfer and the mass transfer, so you see the, sorry, the fresh oxygen fit into the system, into the process is for unit is 30, reduced from 41, okay, which is good. But at the end, only 4 become the discharge, which is very good. From how much? 15 to 4. Because some of it is used for the non-Western students. So it must be consumed by the process one and two as well. But we don't know because not much, not many information given. So this is the report design. So the answer for the challenge one is in here. Yeah, the hydrogen integration. This is example 3. So since hydrogen is a valuable utility gas in crude oil refineries and petrochemical plant, hydrogen reuse and cycle has been the subject of extensive research. Uh, Figure 6 shows a hydrogen network case study where the existing fresh hydrogen consumption is reported. Figure 6 shows a hydrogen network case study where the existing hydrogen consumption is reported at 277.2 mole per second. Mhm. So, purity wise, it has 5% in this. There are 4 hydrogen consumption consuming processes. So we have which consists of hydrocracker, which is seen this one first. We have naphtha hydrotreated HD. This process is correct. So this is for crude oil refineries and petrochemical plant. Mm. They reuse and recycle the hydrogen. Then a diesel hydrotreater DHT, what CNHT. Yes, correct. No, the hydrotreater CNHT system consume hydrogen. There are two hydrogen producing facilities. This one is CRU, the reforming unit here. It produced 415, but the weight is quite high, 50%. Still from unit is RU, 623 kilogram. It is around 7%. And the fresh hydrogen supply, 5%. This is the best. So first need to do the limiting data, identify the sink and the source. So in this case, sink there are four sink. Besides sink. So let's go to this minute. Let's say that medical. So let's spend because of that. Yeah. Good. Thank you. Uh, So we have how many C? Four C. HCU. We have NHT, CNHT, and DHT. The source meaning part of beside the TV, importer. You have CRU, SRU. There are also sources coming from the process that consume hydrogen as well. Although after the consumption, the sum, the concentration of the impurities is quite high, lah. Actually, substitution dapat pilih. Because in the paper is not. Because normally this I know is coming from the diagram lah. Right? Okay. You got it. Okay. Well, well, hmm. The paper said note that the limiting data this table uh, for a hydrogen that cannot be directly extracted from it processed through the game PFD such as in previously, which is what we do previously. Possible here, the detailed procedure to extract the utility data is presented as which paper yang sebenarnya pasang. But it's beyond this scope of this GCA. What I want to know is how to demise it. Okay. So the result of GCA, short mutable segment. Once a job. I skip it. So obviously I shouldn't ever say, but so this is already calculated. The pinch of say at level 10. We read this off. Yes, hydrogen with impurities of 30%. Okay. So the GCT defined NH2 as the pitch closing string from which 354,884 per second must be sent to the region above the pinch. 102.52 must be sent to the region below the pinch. So the value 354,102 is coming directly from the segment GCP. To further reduce fresh hydrogen intake, hydrogen source can be partially treated for use recycled in hydrogen serum. So there are several type of how to purify or method equipment or process to purify the hydrogen with pressure speed adsorption, PSA, membrane separation, cryogenic separation. So each will incur cost, of course, and each will come with different so concentration by how much it can purify the hydrogen, how much it can treat the hydrogen for a second or day, or meaning it's red. You know. So let's see. So given a gas separation membrane with the hydrogen recovery of 95%, which is high, what was solution is to purify the portion of pinch crossing strip CNHT that lies below the pinch. We need a push. So 102, 552. This is referred to table 7 to the product strip at 2% impurities. So meaning once it's treated the 102, that 102 will be a percent. Yeah. So 102 is 30%. So after the purification by membrane, the impurities can be reduced up to 2%. That's better. It's better than the fresh hydrogen imported into the system. So from material balance calculation, the flow rate of this high midstream is 69.57 mole per second. The flow rate and purity concentration for the ejected stream are 32.95 mole per second and 11%. respectively leading these two hydrogen need two new hydrogen source at their resting position will yield a new GCT. So uh, 69.6, this is the high quality Premier reading when you, because the membrane, how it works, it's continuous, but because the pressure is high, so some of the gases, meaning the hydrogen can pass through. So that pass through hydrogen across the membrane is the premier, the high quality, the best one, meaning the 2%. And the remaining inside the system, the membrane system, which cannot go through, the one we call the retentive, and the but and the impurities is very high, very concentrated at 89.11%. Yeah, because just release still has hydrogen inside, but with lot of impurities. So what they do, they put inside the table the GCT instead of this how many level? 11 level, they introduce another two level, one for the uh, permit, another one is for the retentive. But the actual what oh, but the actual 102 will be gone, replacing by the two permit and the retentive. So in this case, the pitch occur now, the recalculation occur at level 12. I can tell retentive. So the fresh feed fired is 196.8. That's perfect. Mula-mula tu buat 77, then without the purification, 268. After the purification, even the fresh water, sorry, fresh hydrogen feed is got lower quality than the uh, purified hydrogen from the last pinch point. That's why the FF is below the 69.6. Next is the purification using pressure swing adsorption. This is another method. So the recovery value is 90% with the quantity of purified hydrogen still up to 0.1%, which is much more impressive than the membrane filtration. So from natural balance, one obtained the product residual product of 64.65, which is the purified one, and the residue from the PSA, it must be a residue, is 37. It's weird to say that. It's not Asia. Here, it is. So you see here, once they do another calculation after the purification to the C2 extra stream, replacing the 102, the pitch occurs at level 12, which is the residue, but the required fresh hydrogen is actually higher compared to the membrane. Membrane only require 196, but if you choose PSA as the purification equipment, purifier, you need 200 mole per second of hydrogen. So, although it can purify up to 0.1%, which is very impressive. So one should note that purifier that give a higher gravity may not necessarily better. That's why we do the GCA before we commit to feasibility study or buy the equipment. We do this one first. Let's see, simulate. A purifier that produce a product at high purity will sometimes be better selection and receive the program that tested. Okay, so this is the multiple pitch. Table 10 show the hydrogen source and simulator or table example 4. So this example 4 also in the paper. Six hydrogen sink and seven hydrogen source of this. The fresh hydrogen supply in this case was with essential of 0.1%. Yeah. Or there's no percent big PFD. So this is sink and this is the source. Okay. Fresh hydrogen supply around 0.1%, which is very good, very pure. Using the GCA, the mineral fish supply is just found to be 125 and 90.96 mole. So FF fish. This is after calculation. This is the fresh hydrogen needed. Tadi berapa? Liter kita. Okay. So it's need 125.1. Here it's a 90.96 discharge. This is a typical multi-pinch problem with two pitch reserve in GCT with the concentration of 1.7 and 5%. Following the ability in water network, the concentration at the lower impurity here of 1% is designated as the limiting pinch. The pinch that influences the overall gas flow rate when any process changes take place. So in problem involving multiple pitches, more than two design region will exist. For example, for the three distinct major design region consisted to a system resistant of relative pitch from 1.7% relative and the secondary pitch at 5%. Here and here, source 1 and source 4. And exact conjunction for having a source in each of the design region, this can be verified using the put this up as a okay. So given so the second pitch we call it a secondary pitch. The first pitch is the limiting pitch. So 1 to 5.1 is based on the limiting pitch. So what if we introduce regeneration with membrane first? So regeneration with membrane we can now needed with the selection. Mm, Identification of the wrong pitch point will result in viscosity during hydrogen network button making. This is very important for problem solving multiple pitches. The region above the limiting pinch is the most constrained part of the network. The bottleneck strategy will only be mentioned when the hydrogen source of chloride is increased above the limiting pinch. Yes, we can. Ultimately, increasing the need of energy for the region of the English mirrors, so the security being if given the set variance mechanism 3, we can now need to build the head selection of the failure technologies to overall reduction chloride. Report GCT for preparing the resource using the classification membrane. So a similar membrane that represents the able to up to represent this. So by introducing this membrane, so in this case, 2% is here with 104. This is not covered in the paper, but by doing the instead, we identify that the premium is around 104 and the entity is 15 with concentration of 64.72%. So the pitch occur at the same level, similar, similar to without the, without the membrane. So meaning since it's below the concentration of 1.1%, so the amount of flash is increased. Sorry, similar. Yeah, similar. But by doing that, we can remove the secondary pitch at 5%, which occurs without the, 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 the purification. Okay. In other words, the achievement is obtained by adding a new element. So, but although you introduce the membrane, there's no changes in FF, in FD. Due to the fact that overall hereditary control by the most muscle particle, which is the region above the limiting pitch, meaning you must targeting something above it. The pitch occur at 1.7, when can go up to 2%. So in this case, you need to use there's no other way. You need to use something better than which is in this case PSA. So by using PSA, because it can go up maybe 0.1% with this. So FF reduced by quite large margin from 125 to 54. The discharge is 1998. Sorry, 19.98. Now the pinch is was at level 10, which is the residue for the PS. So, yeah, there it goes. We can remove the secondary pinch, the debottlenecking. Um, so, we discover meaning, the generation of the gas. You learn about what happens if there are multiple pinch occur. There will be a limiting pinch, there will be a secondary pinch. So there are the bottlenecking there. If you didn't do this, just choose membrane because it's cheap. For example, if you do nothing for the multiple pinch because its concentration is still below the pinch, pitch. So you need to targeting something more than the pitch concentration, which only one on this case lah. Only one option, PSA, could be much more expensive. Alright. So thank you. Uh, I did make you feel better. So the challenges. Yeah, it's just the answer for the challenges one.